So first of all, thank you for this opportunity to present a review on methods combining genomic and epidemiological data in the reconstruction of transmission trees. First, let's start with a bit of context and definitions. In a transmission tree, internal nodes correspond to infected hosts, here H1 to H3. These infected hosts could either correspond to individuals or groups of individuals like a farm, and they are connected by transmission events represented by directed edges, as you can see here. One way to reconstruct an outbreak is the use of contact tracing methods. However, the data collected is not always available, reliable, nor detailed enough for accurate reconstructions. Another way is the use of genomic data, which informs us on the relative closeness of strains. Frequently, this data is applied to the reconstruction of phylogenetic trees. We've talked about it, and these kind of trees are different from transmission trees. Indeed, in a phylogenetic trees, internal nodes are not infected hosts, but hypothetical common ancestors. And the tips, here S1 to S3, correspond to sampled sequences. Inferring a transmission tree solely from genomic data proves challenging. For instance, low evolutionary rates can lead to a limited genetic diversity, and in turn makes it harder to differentiate strains. For example, in a Mycobacterium tuberculosis outbreak, a high proportion of sampled sequences from different infected hosts can be identical. On the other hand, when sequences differ, an incomplete transmission bottleneck and a non-negligible within host evolution can complicate the inference. Thus, methods were developed to combine both epidemiological and genomic data to the reconstruction of transmission trees. So these methods make use of models, and these models can describe four unobserved processes. The first is sequence mutation, which includes substitutions and deletions. The second is within host evolution, which describes how the pathogen genome changes within an individual or a group of individuals and leads to genome diversification. The third is transmission, which is the passage of a pathogen from an infected host to a susceptible one, and the subsequent infection in the newly infected host. Transmission models make assumptions on how the disease was first introduced in the host population, either by single or multiple introductions. They also make assumptions on how it then spread from host to host. And finally, assumptions are made on the natural history of the disease. The fourth process is case observation, which is the process of identifying and sampling infected hosts. So here's our problem. From a real outbreak, represented here by 5 hosts, A to D, and then host U, U stands for unobserved. We can collect epidemiological data such as sampling and removal times from identified hosts. We can also collect genomic data in the form of sample sequences. The question is, how, from these two types of data, how do transmission tree reconstruction methods obtain a reconstructed outbreak? And what kind of models are used, and what are the underlying assumptions behind them? To answer these questions, we systematically reviewed the literature for transmission tree reconstruction methods. Our goal was to discuss methods according to the pathogen studied, the epidemiological data, as well as the genomic data necessary to implement them, and finally, the underlying models. Sorry, I just need to. To do this, we followed a PRISMA method and defined keywords, those pertaining to transmission trees and those pertaining to genomic data. Methods that use solely one type of data to reconstruct transmission trees were excluded, and those that considered epidemiological data separately from genomic data were also excluded. So here's the PRISMA diagram. After removal duplicates, we obtain 318 articles. Among these articles, 87 were the full text of 87 articles were screened for eligibility. We finally obtained 38 articles and identified 20 methods amongst them. From these 20 methods, we defined 3 families according to how genomic data was handled. The first family is the non-phylogenetic family. It consisted of 11 methods, and in this family, pairwise genetic distances were estimated, while in phylogenetic families, a link was established between the phylogenetic tree and the transmission tree, or the phylogenetic tree was used as a source of information. There were 2 types of families: the sequential phylogenetic family of 5 methods reconstructed the phylogenetic tree prior to the implementation of the method, while in the simultaneous phylogenetic families, both trees were simultaneously inferred. So this table here represents the full unobserved processes. Dark blue indicates that the process was explicitly modeled in the method. We can see, for instance, that in the within host evolution column, the few methods explicitly modeled this process. However, most methods made limiting assumptions on the outbreak. For instance, that all cases were observed and sampled in the case observation column, O for observed and S for sampled, or that a single introduction event took place, as shown by the S in the transmission column, or finally that the transmission bottleneck was complete, as shown by the C in the within host evolution column. Here we can see the data necessary to implement the methods in dark blue. Light blue means that the data could possibly be used in the method. We can see that sampling times were used in the majority of methods, so 18 out of 20 methods, while intrinsic characteristics such as predominant species, number of animals, production period, which can be used to describe a farm, were only used in 2 methods. Similarly, contact data is necessary in 2 other methods. 1 second. Here, let's try to select a method according to our previous results and the pathogen study. We decided to consider a foot-and-mouth disease outbreak in a country like the UK. In a foot-and-mouth disease outbreak, the relevant epidemiological units are generally farms. Moreover, wind-mediated transmission could occur, can occur, and could be interesting to take into account. Therefore, we can eliminate methods that consider random mixing. And in addition, it could be interesting to consider geographical data in the form of spatial kernel included in a transmission model. Methods that had a package and that used a spatial kernel were Firestorm's Boris and Hal's Beastleader. In addition, we know that this virus has a high mutation rate, meaning we could want to account for within host evolution. This within host evolution will be accounted for only in Hal's Beastleader. However, we know that ruminants, we know that predominant species could be interesting to include, since we know that transmission generally occurs from ruminants to pigs. This was considered in Firestorm's Boris. So we can see here that considering the data necessary and the type of unobserved process we choose to model, we narrow the choice down to 2 methods. Ultimately, the choice is up to us. Okay, now let's go a bit more into details on how to link a phylogenetic tree and a transmission tree. 3 ways to modify the basic phylogenetic tree were generally used to infer transmission tree. The first method is node annotation, meaning that the internal nodes, were annotated by a sampled host, and therefore we obtain the direction of transmission, but not the transmission times, unless we assume that coalescent events and transmission times coincide. This was used by Coalescent and their work in 2008 and Titus. Here, it's a branch annotation, meaning that instead of considering solely the annotated nodes, nodes that had hosted different individuals, here you can see a node from C and a host from B, this branch was considered an infection branch, and thus transmission occurs along this branch. In this type of way to modify the basic phylogenetic tree, we attain a timed transmission tree. This was used in Duault's work in 2014 and in Hell's Base later. And finally, some methods decided to account for unobserved hosts, and annotated nodes could be annotated by an unknown individual, here U. And this was used in Duault's Philo and de Mayo-Scott. Okay, now let's discuss the unobserved processes. The first unobserved process is sequence mutation. It's important to consider, since genetic distances estimated without a model do not consider back mutations and leads to incorrect estimates. So how is this done? Generally by substitution models. This was used in most families, most of our phylogenetic families. And for the sequential phylogenetic family, it depended on the method used to regenerate the tree. The second process is within host evolution. Ignoring the fact that mutation occurs within host, is not suited to pathogens where within host evolution is non-negligible, such as pathogen with long generation times. In addition, some methods, while allowing within host evolution, only allowed a single pathogen lineage to be present in any host at a given time. Methods that actually modeled the within host evolution used a coalescent process, such as used in Duault's Philo. Another point to take into account is transmission bottleneck, the possibility or not of transmitting genetically diverse strains. So most methods consider a complete transmission bottleneck, as in Hell's Base later, while 3 methods relaxed this assumption and accounted for a weak bottleneck. The third process is transmission. Underlying assumptions of transmission models need to be considered before using a method. Indeed, if one's assuming random mixing, that means that every affected host is equally likely to infect any other host. This could be problematic, as we saw previously in the foot and mouth disease example. Therefore, some methods accounted for random mixing, like in Duault, but others took into account spatial kernel, as in Firestone's Boris, or finally, even included contact data in their methods, such as Campbell's outbreak retreat. Moreover, considering that a single introduction event took place is not suited to endemic situations or in a hospital setting where multiple introductions can occur. Therefore, some methods estimated genetic outliers and considered them to be multiple introductions, as in Molence's work on rabies. while others actually model the disease introduction and the methods as in Warby's bit rows. The fourth process is case observation. Considering that direct transmission events links are sampled hosts could lead to false estimates on the natural history of the disease or even false transmission links. Therefore, some methods considered a proportion of observed cases in their methods, as in Duault's outbreaker, or model test sensitivity, as in Warby bit rugs, or finally took into account a maximum number of hosts in the outbreak, as in the myoscopy. This case observation is interesting to model when we can possibly miss infected individuals. So the pathogen study, the detection protocol, as well as their effectiveness needs to be considered. Sorry. So in conclusion, and as a take-home message, we considered the epidemiological data necessary to implement transmission tree reconstruction methods. We defined 3 families according to how genomic data was handled, and considered that the choice of a method depends on the unobserved processes we wish to model, therefore also depending on the pathogen study, the case detection protocol, and the epidemiological units considered. The impact of violating underlying assumptions can have on the reconstructed transmission trait could be interesting to further investigate. Thank you for your attention, and thank you, Benoit and Laetitia, for your help. If anyone is interested, there are 3 slides of references. Go.
Non, c'est très bien, c'est vachement timely, voilà, comme disent les Anglais, comme étude, parce qu'il y a plein de méthodes. J'avais une remarque sur les mots-clés PRISMA, parce qu'il y a notamment une étude de l'INRA d'Avignon, Samuel Souberan, de la UTEGO, qui fait des codes pour 3, les 2. Et j'ai regardé vite fait l'abstract, et justement, ils n'utilisent pas de transmission tree. Donc peut-être qu'il y a moyen dans les mots-clés de pouvoir peut-être rattraper. C'est vraiment un travail. C'est important, je pense, de comparaison entre les méthodes qui ont tendance à pas trop le faire. Et si j'avais une question, pardon, est-ce que sur les méthodes, c'est toutes des méthodes avec des données Sanger, enfin des alignements, ou est-ce que parmi les méthodes, il y en a certaines qui utilisent des données illimitées, travailler avec un peu intermédiaire en fait entre purement du SNP sans phylogénie et des phylogénies. Enfin, je pense notamment à la méthode d'Avignon, et ils travaillent directement sur des châssis. Je ne sais pas si parmi les types de données qui avaient pu se pratiquer en fonction du type de données de séquençage.
J'avais pas vraiment regardé là-dessus, c'était vraiment juste des données de séquençage. Ça pouvait être whole genome sequencing, ça pouvait être juste un gène ou un. Le but c'était qu'il y ait juste des données de séquençage et que ce soit sous forme de SNP. Pas de. Parce qu'il y en a qui ne prennent pas la séquence consensus, mais qui prennent un seul site et qui regardent les différentes trucs du deep sequencing. Et ça, j'ai écarté, je ne suis pas allée dans les détails là-dessus. Ça devenait un peu compliqué.
Juste pour rebondir sur la question de Samuel, il n'y a rien, vous n'avez rien développé avec Emma
on n'a pas publié.
C'est pas publié.
On fait juste la phylogénie pour le moment, mais on peut mettre les séquences, mais je ne crois pas qu'on ait publié quoi que ce soit. On utilise les données. On fait ça.
Donc la référence à laquelle vous avez mis Samuel, c'est à la 2019. Tu veux retrouver.
Je crois que j'avais
C'est
déjà
la
regardé.
méthode systematique.
Ok, merci.
Yes, just a question about potential issue with these methods. I think that there was some people in the literature who were interested in seeing whether when the infection process is quite long, actually you could have some problems if you do not sample the genetic diversity of the pathogen always at the same period of the infection. You could have some issue to try to reconstruct the transmission chain because there was some mutation that accumulates and potentially a lot of mutation that can accumulate from the beginning of the infection to the end of the infection. And I wonder whether actually this issue has been solved with some methods or whether you didn't see any methods that tried to tackle this issue.
I haven't seen any methods that consider the timing of the sampling compared to the natural history of the disease.
At least that try to take into account the length of the infection time, which can be for some disease quite long, and cause some problems to try to see which sample should look like the other.
Well, some model time to sampling in their methods, while within host evolution, there are some that have the possibility of taking into account multiple sequences. That's very few methods, and there remains a big problem on within host evolution. And some, as you can see, most methods disregarded within host evolution completely. So yeah, I don't think anyone has that method, that problem. Thank you.
Particulièrement dans le cas de la tuberculose bovine, est-ce que, typiquement, c'est une question qui peut se poser, puisque c'est une maladie qui a une histoire très longue. Est-ce que tu as identifié des gaps dans la littérature, des choses qui sont manquantes, qu'il faudrait développer, qui ne sont pas prises en compte par les méthodes que tu as analysées?
La plupart des méthodes considéraient de la même façon une maladie virale qui évolue rapidement qu'une maladie bactérienne qui évolue lentement. Et vous pouvez utiliser des méthodes qui, justement, encore le problème de l'évolution de la bactérie. Mais oui, la plupart du temps, il n'y a pas de distinguo entre les deux. Et je trouvais ça un peu gênant, mais je ne pourrais pas, je pas de plus là-dessus.
Moi, j'ai plus de questions par rapport à l'application de ces méthodes. J'en sais qu'il y a beaucoup de papiers qui lisent différentes méthodes, qui prennent en compte différents critères. Et en fait, après, je ne les vois pas souvent appliquées pour des épidémies données. Parce que j'imagine que c'est pour utiliser vraiment des tout petites données où on a des données très précises sur, je sais pas, 10, 15 foyers. C'est rarement le cas, parce que dans cette épidémie, il y a beaucoup plus de foyers. En fait, j'arrive pas à voir dans quel cas on les applique pas. Parce que souvent, c'est développé sur les données de FMJ où on sait très bien où elles sont, ou à cette mais après, j'arrive pas à voir. Je ne sais pas si tu as vu des applications, d'autres papiers où ils appliquent en fait ces méthodes.
En fait, du coup, j'ai fait effectivement la liste de toutes les différentes méthodes et de leur application sur. Mais c'est souvent les mêmes qui reviennent. C'est la tuberculose, le MRCA, c'est la fièvre, c'est et il y a la rage, il y a quand même beaucoup d'applications. Mais oui.
Je ne sais pas si ça peut t'intéresser, mais je crois que c'est une fois qu'il a mis sur Internet, il a regroupé des données, en fait, la chaîne de transmission est commune et où il y a les séquences correspondantes pour valider les méthodes. Mais je ne sais pas s'il y aura des données sur le lien pour savoir si on infère avec une chaîne de transmission. Il a regroupé comme ça, mais il aurait dans les données totalisées, il y a des cas où on est à peu près sûr de la transmission et on a aussi des données suivantes qui sont bien pour vérifier que les méthodes fonctionnent.
Pour prolonger cette question, la question d'avant, sur Covid, il n'y a pas eu, la présence d'esprit sur le Dan Princess de récupérer les échantillons et les kilos.
Il y a eu des...
Parce que dans un système clos, quoi. En fait, le problème, c'est ça, c'est ces méthodes-là, elles sont bien quand on échantillonne à un taux très fort, quand on en remplace peu. Sur le moment où on échantillonne un promille de ce qui circule, c'est plus les mêmes méthodes. C'est des méthodes phylogéographiques qui s'appliquent une liste. Et je me posais la question, s'il y avait des échantillons sur ce genre de système clos.
Alors, sur le Covid, j'ai vu passer surtout sur Wuhan, j'ai pas vu d'autres feuilles qui étaient étudiées. C'est souvent le même.
Il y a des publications où ils ont mis en évidence du super spreading en analysant un outbreak très fin. Mais je ne crois pas que c'était en utilisant des armes de transmission. Je vais peut-être regarder ça.
Du coup, c'est que en santé animale.
J'ai pris toutes les méthodes.
Et du coup, les données, c'est que pas en santé humaine.
Si, il y a des données en sentiment. Il y a le MRCA, le staphylococcus dans des hôpitaux. Et la tuberculose aussi, chez l'homme qui est étudiée.
Sinon, tu as cité l'article de Firestone 2020. Tu connais celui de Firestone 2019?
C'était la comparaison par rapport à un nombre limité de méthodes sur la fièvre aqueuse.
Ouais.
À des simulations de fièvre aqueuse.
Et c'est quoi, parce qu'il y a sous les yeux, il y a une quinzaine de méthodes, une dizaine de méthodes qui sont listées. Il y a un tableau avec plein de critères qui ressemblent à cette famille. Du coup, si tu compares les deux, est-ce que toi, il y a des critères que tu as regardés, qui ne sont pas regardés dans ce papier?
Ils ont un tableau comparatif. Ouais. En plus, ils étaient focalisés vraiment sur la méthode en elle-même. En plus de ça, j'ai rajouté toutes les applications que j'avais trouvées dans la littérature. Pardon. Et je suis allée un peu plus dans le détail sur les modèles de transmission. Quels sont les états qui sont considérés. Et vraiment, oui, c'est dans le détail. Là, c'était vraiment, si je me souviens bien, c'était est-ce qu'on prend en compte ou pas l'évolution d'un throat, ou est-ce qu'on prend en compte un transmission bottleneck, mais ils ne sont pas allés dans les détails des modèles qui sont utilisés derrière. Et donc, bon, là, je n'ai pas présenté parce que présenter une à une tous les détails des méthodes, ça allait être un peu long, mais oui, voilà.
Merci beaucoup.
Merci.